here's the definition. We established a bunch of properties. And so basically they're you know, how many are there here? 8 properties that are kind of trivial, or say not hard. And 1 or 2 that are actually deep and interesting. And so these are the less deep ones. The interesting one was this, which is both a weak, strong uniqueness theorem and a control of instability. And so we define this magical vector field. So the idea is, given a smooth curve, a smooth solution little gamma, we build a vector field x sub gamma out of it. And then we use that to define a functional. This, I've written it here as E. So this is like the relative entropy of the rough curve V, the varifold, with respect to the smooth curve little gamma. And it built into it is a radius R, which is like the injectivity radius of little gamma. So within a tube of radius R around gamma, there is a unique closest point on the curve little gamma. Okay, and so then there's this, and so we saw this, that this quantity, we can think of it as being a sort of a distance of the rough curve, V, from the smooth curve little gamma. The main theorem is that if I define, say, capital F of t to be this notion of distance between the rough curve and the smooth curve at time t, then we can control the growth of that thing. So it grows exponentially. So here are the constants. You know, there's this, I have this injectivity radius R, and this constant here depends on R. And so as the first time of a self-intersection approaches, the constants will blow up and this estimate loses any strength. And so this is only valid until, as long as there's no self-intersection. Okay, and so this in particular has weak, strong stability. A weak solution that coincides with the smooth solution at time 0 will continue to do so until the first time of self-intersection. And the key, and the proof boiled down to this pointwise inequality for this vector field x sub gamma, capital X sub gamma. Okay, and so this is what we were doing at the end of the hour last time. And what I want to do now is to return to the Euler equations. And the goal is to say, and I'm going to, for the next day or two, I'm going to skip a lot of calculations and summarize things, because otherwise we would spend a week or two, or maybe 2 or 3 weeks, just doing calculus. And so I'm going to omit almost all the computations. But anyway, here's so the goal is now to return to Euler and say something, if we can, about the connection between these two equations. And remember, the idea is that we have this similarity between these two identities. And so far what I've said is just, well, they look kind of similar. What I would like to argue first formally and then more carefully is that if I somehow know, if I'm given a velocity field u epsilon, and I somehow know that the vorticity of u epsilon is concentrated around a curve, and I have some other information, then that will allow me to conclude that, so if I somehow know that, say, let's ignore t, if I know that the intervals on the left-hand side, if omega epsilon is concentrated around a curve gamma at some time t, and I have some other information, then in fact, it will follow that the right-hand side here looks like the right-hand side there. And so this will strengthen the formal connection between the two, and eventually allow us to prove it. And the theorem will eventually prove, will say, it does not by any means establish the existence of solutions of the Euler equation with vortex filaments evolving by the binormal curvature flow. But what it does show is that in this certain asymptotic regime, the binormal curvature flow is the only possible. It says that if there is some kind of law of curve motion, it must be the binormal curvature field. This is roughly what the theorem will say. And that's progress. That's still far from what one wants to know, but it's better than nothing. Okay, so and so there's a formal argument which I'll give actually below, and it has drawbacks which I've mentioned here. So let's sketch it. And so remember earlier we had a formal argument. There's this kind of classical formal argument which essentially goes back 100 years for the connection between the binormal curvature flow and the Euler equations, and it goes as follows. It says, consider a perfect vortex filament. So take a measure living on a curve. Okay, that's too singular, so we can mollify it by convolving with a kernel. So now it occupies a tube of scale of radius epsilon. Okay, so we have this epsilon, this sort of perfect filament on an epsilon scale. And then we can use the Biot-Savart law to, and so our idea as well, if we know how this epsilon tube moves, we know how the filament moves. And so we look at the boundary of the tube and we compute the velocity of the, at least we approximate the velocity by using the Biot-Savart law to reconstruct the velocity from vorticity. We approximate the velocity at any such point, a distance epsilon from the tube. And so to do this, we just do a second order Taylor expansion of the, well, okay, let's put it this way. So the first thing is that by properties of the Biot-Savart kernel and the way we've regularized, the velocity field a distance epsilon away from the filament exactly coincides, the velocity field associated with the regularized vorticity exactly coincides with the velocity field associated to the singular vorticity. Okay, so that makes computations easier. So we're just computing the velocity field associated to this singular vorticity living line curve at a distance epsilon from the curve. And so if you just do a, so they used to do a Taylor approximation curve, a second order Taylor approximation. And if you just look at the first order term, it's like computing the, if you look at the first term, you get a straight segment. And then we sort of cut it off at a certain distance. And so this is, well, yeah, so this is what it is. And one can compute that rather easily. That computes, so imagine we're in the midpoint of the straight segment. By symmetry, there's no vertical component to the velocity. If I imagine the segment's ordered in vertical direction. And so the velocity will be purely rotational. And one can see rather easily that its order is of order 1 over epsilon squared, 1 over the distance squared from the segment. Okay, if the segment is close to length of order 1, then this same asymptotic will hold for, you know, as long as the length of the segment is large compared to the distance from the segment. Okay, so if the segment is length of order 1, this would be valid for distances up to, you know, little over 1. And that doesn't tell us anything about how the curve moves. If it's purely rotational velocity, it's not going to. So the idea with all these things, which we saw also in 2 dimensions, is that a purely rotational velocity doesn't move the vorticity anywhere. Okay, so then instead we do a second order Taylor approximation of the curve, and then what you see is that when you do that, the Biot-Savart kernel says that, well, the leading order velocity is still purely rotational, as exactly as before, with magnitude of order 1 over distance, so 1 over epsilon if I'm distance epsilon or smaller. Then there's a correction term whose size is of order log epsilon, and so the rotational part, you know, if I'm at different points on this tube, it'll be pointing in different directions. The correction term is always pointing this in the same direction. It's pointing in the binormal direction. Its magnitude is of order of log epsilon, maybe over 4 pi, and is proportional to the curvature, to the which comes from the second term of the Taylor approximation curve, obviously. Okay, that was the argument we saw before. And so the basic idea was, well, you know, take this filament and modify it and create a perfect epsilon vortex filament. And so for a new form argument to consider things in this setting, I'll start by doing the same thing. I'll say, well, let's take a, what is this? my notation is a bit different. Let's fix the notation. So before I said, I think I called this omega sub gamma, and this was omega sub gamma epsilon. And okay, and so if we have a curve little gamma, parameterizing smooth curve capital gamma, then we wrote omega sub gamma. I think I had arrows here to denote the measure, the vector value measure corresponding to integration along the smooth curve gamma. And then omega gamma epsilon was that thing modified by convolving with a radially symmetric kernel supported in the ball radius epsilon. And so then, and so again, I'm assuming for purposes of this formal argument, a perfect filament. I take this thing and I look at the velocity field that is generated by the Biot-Savart law. And I know, as before, that outside the tube radius epsilon, this coincides exactly with the velocity field generated by the unregularized, by this omega sub gamma. Okay, and so then one can easily check. So I'm looking at the terms. So for the Euler equation, this term and this term were the two things appearing. So we had ddt of the thing appearing in the first equation of this was equal to that. And then on the right, and then for the binomial curve, we had these geometric quantities. Okay, and so first I claim that the vorticity is very close to being, if I look at how it acts on smooth functions, it's close to just integration around the curve gamma. Okay, here's, I should have written gamma at time t. Actually, let me remark, in the previous formal computation, we did a week or two ago with the second order approximation. So what we do is we fix the curve, which we imagine is the curve where the vorticity is concentrated at a certain time, and we compute the instantaneous velocity. And so time doesn't play much of a role. And the only role that time plays is that we can compute the velocity with it, but that's a purely that involves integration only in the x variables, and then we interpret the computation saying something about the velocity of things. Okay, and so here too we assume that we know the vorticity at some fixed time, and we're proving things about it. Okay, and but it's easy to see. So yeah, this. Well, let's see if we can do this. Yeah, this is totally straightforward. I want to prove some things. So omega epsilon, by assumption, is this perfect filament. It's rho epsilon convolved with omega gamma. So this is really okay, and omega gamma corresponds to integration of the curve. And so then the integral of phi of x dot omega epsilon of x dx will be phi of x rho epsilon of x minus y dot omega gamma of dy. We can write it like this, and so this is phi epsilon of y dot omega gamma of dy. Okay, if I integrate first in the x variable, use Rabini's theorem, where this is and phi epsilon minus phi is bounded by the so I'm averaging a smooth function at each point over ball radius epsilon. That'll change its value by most epsilon. And this is just the integral of phi epsilon around the curve. Well, so it's sorry, it's and this is just the integral of phi around the curve gamma. That's how we define that measure. Okay, and so this first identity is trivial. And here I've just written in different notation, the right-hand side. Okay, and so and then I claim, and this is the kind of computation I will repeatedly omit. But I claim that, well, I said this a little while ago, that for just a first-order Taylor approximation of the so if I want to estimate the the velocity field, I have this curve gamma. I can just approximate it. So I can do a first-order Taylor approximation of the curve gamma and use that to get an approximation of the velocity field. And this is what we said. It's at any point near the curve, the velocity is purely rotational, and it scales like 1 over distance. And here, so earlier in the previous argument, we said this was true at distance epsilon, but this is true for a range of distances. As long as again, as long as I can approximate the curve, I look at a segment of length, say 1 over log epsilon. So almost order 1. And so because it's shrinking as epsilon goes to 0, the Taylor approximation will improve. And I'll get some I'll benefit there. But then if I look at the distance 1 over log epsilon, that's small compared to this 1 over log epsilon. And so on this scale, I can justify, and I can be a little more careful and actually keep track of errors. Okay, and so then from this one can then estimate the term involving U tensor U. And what you would see if you do the calculation carefully, and I think I'll always, well, let's see, let's look at this. Okay, how would I do this? So I claim that if we do this computation carefully, then we will find that the integral of the velocity field generated, if I let it act on a test function, it looks like I evaluate the test function along the curve. Well, okay, so the first claim is that the almost all of the L2 norm of the function here lives in this region here where I have where the above description of the velocity field is valid. Okay, and so so there are two assertions. The first is that we can throw out the velocity field in the epsilon tube around the curve gamma, and we can also throw out the velocity who's beyond there, who's outside this 1 over log epsilon. Okay, within the epsilon tube, that's pretty easy to see. And so the point is that what's the point? One can see pretty easily that the velocity everywhere is bounded by 1 over epsilon. So I have this. So the velocity everywhere is bounded by 1 over epsilon. And so within the epsilon tube, I have, or is it 1 over epsilon squared? I think it's 1 over epsilon. Right. And so within this tube, the vorticity, one has a rather straightforward bounding velocity, and then the volume of the tube is simply the length times epsilon squared is the cross section, and so that's easy. Also, it's only far away. Essentially, the velocity is bounded and it decays, and so we can throw out this as, and so the other, and so the point is that this integral here, this whole thing is scales like is diverging logarithmically, and so this approximate sign means, well, the whole thing is diverging logarithmically, and the part I'm throwing out is diverging more slowly than logarithmically. So that's the first claim, and then the second claim is that this the integration within this tube is exactly this. So remember, this 1 minus tau tensor tau is projection onto the normal space. This get into. And so let's see if we can believe that. And so first of all, okay, so I'm integrating, let's assume phi is C3 or C2 with some modulus continuity. Let's say C3. Then the gradient of the curl of phi is still Lipschitz. And so integrating around a tube whose integrating points at most 1 over log epsilon from the filament. At such points, the gradient of the curl of phi will differ from the point on the nearest point on the curve by a constant over log epsilon. Okay, so first I can approximate so also okay, and so these are combinations again, well, mainly later on. So the integral for let's call this set S epsilon, the integral of the gradient of curl of phi U tensor U is equal to the integral over S epsilon of the gradient of the curl of phi at X. Here I'll look at the point P of X, which is a point on the curve, the closest point on the curve. Okay, times the L2 norm of U. And the L2 norm of U it turns out to be of order log epsilon. And so this whole thing is order 1. Okay, that's the first approximation. And the second is and so let me so I'm integrating over this region, which is a big cylinder minus a small cylinder. And at every point in this region, I have a unique closest point on the curve. And so what I can do is I can just integrate over the curve gamma. And then I look at the points S epsilon, the points in this thing. And I look at the P inverse of X. And then I integrate the same integrand. And I get some kind of a factor from the, so here I'm using the co-area formula. And so what happens, I get some sort of a factor with some times, so there's some Jacobian D sort of 2, that's the fancy way of writing D area, and D Hausdorff 1 of X. Okay, and so so I guess I'm kind of Jacobian. I've changed variables, and that this is well. So this is it's smooth and it equals 1. Let's say it's Lipschitz. it equals 1 on gamma, and so it's 1 plus the low of 1 in S epsilon. Okay, and so I can approximate this by 1. So this is measuring the. You see what I'm doing is I have this curve. I'm integrating over these slices, and what I'd like to do is pretend that the slices are parallel. That the volume is the volume of the slab is exactly the volume as it were in a cylinder. Okay, and so. Okay, and so then I would. Then I would just approximate this by 1 plus some error terms, which again are order 1, I believe. So this should again be 1 over log epsilon, the errors I make when I do this. Okay, and so then I just have to integrate. So I have the gradient of the curl of phi, and I just have to integrate this matrix. I have to integrate this U tensor U over a. So I'm at a point on a curve. I'm integrating over a slice who is normal to the curve, and I have this. I have this approximation from above. I know that to leading order in the slice, the velocity is purely rotational, and scales like 1 over distance. And so, for example, it's easy to see that the and so this one can do explicitly. And this is. I think this is right. Okay, and so the first claim is, well, let's see. There's a. Okay, why is the Jacobian equal to 1 on gamma? Someone asks. Good question. So let me see. To actually do the calculations is kind of tough, but let's put it this way. And so again, so suppose that the if the curve were really a straight line, then well, okay, I'm gonna not answer this question for now. Let's finish the calculation. Let me. I'll see if I can do it in an easier setting. Okay, so then if we accept this claim, then I assert that this is believable. So what are we saying? So let's imagine that that the curve is vertical, and so I'm looking at points in the xy plane in the normal plane of the curve. So I approximate the curve by a line. I look at points in the normal plane, and I know that the velocity is exactly this rotation thing. And so I can see first of all that that this integral, so the u3 components, the vertical components are 0, and so when I have an integral of u, so this is, so if I call the components ux, uy, uz is 0. And so clearly the integral of uz times ux, uz times uy is 0. So equals 1, 1, 0, 0, 0, 0, 0, 0. If tau is okay, so if the vorticity is vertical, the claim is that this this integral will give me this. And so the first one is that, well, the vertical components of the velocity vanish, and so for sure the vertical components of the and so, sorry, we're replacing this by y perp over y squared times 1 over 2 pi. Tensor itself. Okay. Okay, and so then in this case, you know, y is just a vector. I'm integrating over the xy plane, and y is the rotate vector. I can see the vertical components vanish. Anything involving a vertical component, and so the two diagonal components should be equal. There's no reason to have a. Okay. Okay, and so this is really a matrix. If you write it out, it's, and so here's a d y. This is y2 squared, y1, y2, y1, y2, y1 squared, 0, 0, 0, 0. Okay, when I approximate the velocity as I have, then this is the thing I have to integrate. And I'm integrating for epsilon less than y less than 1 over log epsilon. This is all divided by y to the 4th. Okay, and so parity considerations will tell us that the y1, y2 integrates to 0. You can actually you can do this polar coordinates if you like. This is this is 1 over 4 pi squared, 1 over r squared, and then what is it, sine squared? Sine theta, cos theta, the same, and then cos squared theta. There may be a minus sign there. I don't care because it's going to vanish. 0, 0, 0, 0, 0. R d theta. R d theta. So that's, we can see this will equal exactly something of order. I may have the constants a bit wrong, but there'll be a log epsilon. So the sine squared and the cosine squared integrate to, that'll give us a factor of, that's right. So when I integrate these will integrate to 0, and this will integrate to pi. And so the pi cancels one of these things, and I'll get a 1 over 4 pi. And then the I just integrate r, integrate 1 over r from 0 to, or from epsilon to log epsilon to the minus 1. And if you do this, you see you'll get what I asserted up here. So that's how this computation goes. We have to throw at the core, throw at the faraway stuff, approximate the Jacobian, and then the integral we can do explicitly. And but the point is that, well, the vertical components vanish leading order, and the u1, u2 components cancel, and then the u1 squared and u2 squared components are equal to leading order. Okay, so so this is a form argument in a different style. So it and I'll see if I can say more convincingly why this Jacobian equals 1 to leading order on gamma. Okay, but so here's the point. So I've assumed a perfect vortex filament, and earlier I said, well, let's compute the velocity sort of pointwise by using the Biot-Savart law. Here I said, well, let's compute how it acts on a test function. And what we find is that it acts on a test function, and so we know that if we know how to act on a test vector field, well, so we've seen that the action of the vorticity, I mean, that the we have this expression, the integral of phi dot omega, and we know that. So essentially, what we're showing is the way the vorticity acts on a test vector field is the same way that a curve moving by the binormal curvature flow acts on a test vector field with errors and up to this rescaling in time from here. Okay, and so this is a different way of understanding the sort of a different formal argument for the relationship between the binormal curvature flow and the Euler equation. And okay, so then so the goal now is to say something more rigorous. And let me point out an interesting thing. So I've at least sketched two different formal arguments for the link between the Euler equation and the binormal curvature flow. The first relied on a pointwise computation of the velocity on a tube of radius epsilon, where we needed to do a second order Taylor approximation of the velocity field to find the binormal curvature flow. The second relied only on a leading order Taylor approximation. I only need a first order Taylor expansion. I only need to know what the flow is doing, not at a distance radius epsilon, but in a sleeve of thickness epsilon out to almost order 1. And I need to know what it's doing in an L2 sense. And I get the same conclusion by looking at rather different information. That's interesting. Okay, but again, this argument, like the previous one, says, well, if we have this perfect structure at a certain time, we can compute the instantaneous velocity at that time, or we can approximate it. But it's not a very satisfying argument mathematically. And so, so what one would want to know to prove the theorem, to really establish this vortex field conjecture, is one would like to. So one way to think of it is, I'd like to identify a class of vorticity configurations. And I'd like to know that this, and it's a class within which I can compute I can approximate the velocity of so it's configurations where there'll be, where I can associate a vortex filament or a curve around which the vortex is concentrated. I'd like to identify such a class. And I'd like it to have the property that I can compute the velocity and find that the, it should be like the binaural curvature. And I'd also like to know that this class of vortex configurations is stable with respect to the Euler equations. If I knew that, I made all these assumptions about the vorticity structure. If I had weaker assumptions and I knew that, and I could show that if these hold at time 0, then they hold at later times, then I would be in business. And so this is what we did with point vortices in the Euler equation in 2D. We said, well, we'd like to imagine, what we showed in fact is that we looked at point vortices with vorticity supported in a, well, we assumed it was supported in the ball of radius epsilon. But we showed that if essentially we showed that if it's supported in the ball of radius square root of epsilon, or a bit bigger, and we have control over the second moment, then these properties are preserved by the flow. And that was the crucial step in proving the validity of the point vortex approximation for the Euler equation. So we had this this set of vorticities that was stable with respect to the Euler evolution, in which we could compute in which we could justify this point vortex approximation. Okay, and so then, okay, and so the goal is to at least justify this computation of velocity for a larger class of vorticity configurations, and then to actually have estimates instead of all this, to have real estimates instead of this hand-wavy stuff, and to use that to attempt to establish a rigorous connection between those two things. Okay, and so my goal then is justify this computation for a larger class of less perfect vorticities. And then use this to say something about Euler. Something rigorous for once. Okay, and so okay, the larger class. And so here's what was unsatisfying about the. I mean, every computation I've done for Euler so far has had the same structure. I assume a nice C2 curve, and I make it. I assume really an explicit description of what the vortex looks like. I take a measure and I convolve it with a radial multiplier. That's not good. And so the ways I can weaken this would be, well, one thing is I could have less stringent requirements on the curve. And then I can have a weaker description of vorticity, concentration. And so I would like to then, I would like first to justify computations of this sort under these. I would like to relax things this way. Okay, let me talk very briefly about the first. So I'm following here a paper that I wrote a while ago with a collaborator, Christian Zeiss. And so we spent some effort on this. I'm not going to spend much time on it because it's a bit technical, but let's look at it anyway. And so here's the idea. Oops. Anyway, so here's the idea. So before we assumed this injectivity radius, R gamma is positive. So there's a tube around the curve within which there's a unique closest point on the curve. That's actually good enough for most purposes. That's if the parameterization is C2 and if it never comes. So there are two issues. One is if the curve has corners, that's not going to happen. If the curve fails to be C2, if it's only C1 alpha, then the injectivity radius will drop to 0 at certain points. And the other issue is, well, it may be perfectly smooth, but it might come back and intersect itself. So there's a local and a non-local obstacle to this injectivity radius being positive. That's actually good enough for most purposes. But nonetheless, let me just describe briefly a way of weakening this. And so this is what I'm going to describe is sort of the, okay, it's a bit technical, but in a way it's the natural thing to do. And so here are less perfect filaments. And so the idea is I want to define an injectivity radius at each point S on the curve. And so I suppose I have a curve that looks like this. Let's make it be black. I can say, well, I can define a tube of varying thickness around here. And clearly the thickness should drop to 0 where the corner is. But I can define a tube of varying thickness within which there's a unique closest point. Okay, and so at each point S on the curve, at each point on the curve, so the curve is parameterized. At each point, I can define at the point gamma of S. Oops. So if I have some point here, which is gamma of S, I can define a radius R sub gamma of S, which is the radius in the normal slice at that point. Okay, so we have a way of doing this, and And then a measure of the regularity of the curve is, well, we can look at the, well, here it is. Okay, so I define this, this thing, or gamma. Let's not look at the definition in detail. And then I will define kappa, sub gamma, kappa star. This is like the, it's sort of a weaker version of the curvature. And so it's 1 over this radius. And so here I would say the curvature is infinite because the radius tends to 0. And here the curve, I mean, this sort of curvature. So it's this takes account of possible self-intersections. And so at points where even if the curve is perfectly smooth, if it has this, if it comes back and intersects itself, if both branches are smooth, still this, I would say, the curvature is infinite. Okay, and so then we define, we measure the regularity of the curve by looking at some norm, the weak L1 norm of this thing. And so note, let me just say, this allows for corners and it allows for self-intersections. It allows for limited corners, limited self-intersections, the finiteness of this quantity. And so that's a kind of a natural class of curves to consider, because you see, all I'm doing in these computations is I'm looking at normal slices and I'm doing computations within these normal slabs. And if I can control some integral properties, like how big is the slab, how big is the normal thing overturning, that's good enough. Okay, and so, but the point is, when I start saying theorem, I need some kind of qualitative, I need some kind of measure of the regularity of the curve. And this is one. Another one would just be the, I could assume more. I could assume there's an injectivity radius, and then the relevant quantity would just be 1 over the injectivity radius. That would be the, and so in particular, if there is injectivity radius, then this kappa 1 star is less than. If there is a global injectivity radius r gamma. Okay, and so that's so let's think of it as being this, if you like, but there's a more natural thing. Okay, and so then what I'll do is state theorems in which this quantity appears, and so we'll just see this as, again, something who controls the regularity of the curve, who is like, if you like, is comparable to the size of the tube around which I have a unique closest projection. Okay, and then okay, this is a good place to stop. And so well, actually, no, there's a question earlier, why is the Jacobian equal to 1? And so this actually addresses this Jacobian question. And so the well, okay, so the answer to this question is there's a computation, and maybe I'll say more about this on Wednesday. But so the remainder of this discussion is, well, there's some theorems, and the theorems are basically out of calculus. And so, and I've done sort of very hand-wavy versions of the main ingredients. And so what I chiefly wanted to do is to sort of feel like we're comfortable with statement theorems and to refer you to the literature if you're interested for the details of the calculations. And there's some main points that I'll do more carefully. And we'll see how much we can finish of that on Wednesday. And then finally, I'm hurrying through this a bit because I want to say something about the 2D point vortex dynamics for the Gross-Pedievsky equation. So the other model of ideal quantum mechanical fluid flow in this flow. Okay, so let me stop here, and I'll hang around for a few minutes in case there are any questions. And okay, I'll also put this in the chat. This file, and this file also contains a preview of what we will discuss on Wednesday and maybe Thursday as well. So let's do this. Upload to Dropbox. Oops, that didn't work. So maybe let's try again. Okay, and now I should be able to put this in the chat. Let's see, what's it called? There it is. Okay, so download that if you like, and I'll stop the screen share.